On to chapter 4. Okay, chapter 4, probability distributions, PDFs for a discrete random variable. So there's two characteristics that define a PDF. One, each outcome's got to be a chance between 0 and 1, and the sum of all the outcomes has got to equal 1. And that's it. So 4-1 is not too bad. So this is kind of homework from 4-1, 10, 11, and 12. Use the following info to answer the next 3 exercises. Ellen has music practice 3 days a week. She practices for all 3 of the days, 85% of the time. 2 of the days, 8% of the time, and 1 day, 4% of the time. And a bad week, no practice, 3% of the time. So you're gonna choose 1 week at random. First of all, what are we gonna assign? Define capital X as. Capital X will be, so let X be the number of days in a week that Ellen practices. So little x, blah 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 blah. Little x can take on 0, 1, 2. What else do we got? 3. So 3 is the highest. Okay, so 11. Construct a probability distribution table for the data. So here we go. We've got x, which is 0 days a week, once, twice, and 3 times. And this is the chance of x happening, the probability of x. 0 is 0.03. 1 day a week is 0.04. 2 times a week is 0.08. And 3 times a week is 85. So each outcome falls between 0 and 1. If you add them all up, 85 and 8% is 93 plus 7, so they sum and give you 100%. So 100% of the data is falling between 0 and 3 days. Okay, so 12, we know for a PDF it's got to have 2 characteristics. One is that the sum of each outcome is 1, and we just did that. If you add all those up, that equals 1. The other characteristic is that each of these individually has got to be between 0 and 1. And check, so we're in business. Okay, so problem number 69 from your homework. Suppose that this PDF is representing the number of years that it takes to earn a Bachelor's of Science degree. So BS, that's usually a 4-year degree from any college, university. Okay, so A, in words, define the random variable x. So these are little x, 3 years, 4 years, 5 years. So big X is going to be the number of years to earn a bachelor's. Okay. B, so if you're looking at this table, what does it mean that little x, oh man, little x does not equal 0 or 1 or 2. So that means this, it is not possible, not reasonable to earn a BS in 0 years. 0 years is impossible. 1 year, I guess depends on how many credits you graduate high school with, how much concurrent enrollment you got. 2 years, you might be able to earn 1 in 2 years. But typically it's not reasonable to earn a bachelor's in 0, 1, or 2 years. Okay. Okay, now for 2, the mean, or the expected value. So these two are kind of the same thing. So the mean The expected value or mean, so they're the same thing. Of a discrete random variable predicts the long-term results of a statistical experiment that has been repeated many times. Standard deviation of a probability distribution is used to measure how much each outcome varies from the mean. So it's kind of these fancy formulas. The expected value is the summation of x times the probability of x happening. So this one will make sense. This one's not too bad. Standard deviation, that one, I don't even know if we ever did it in your homework. This one's kind of not, you're gonna have to use a formula for that, but this expected value is not bad. So here we go. So 71 from your homework. A game involves selecting a card from a regular 52 card deck and tossing a coin. Coin is a fair coin and is equally likely to land on heads or tails. So here are the outcomes. The card is a face card, and heads, you win $6. Face card and tails, you only win $2. If the card is not a face card, you lose $2 no matter what the coin shows. Okay, so find the expected value, find the average. So let's do this. Let's make a distribution. Okay, now I'm gonna maybe do 3 columns. No, I'm gonna probably do 4 columns. So this is x. This is the probability of x. And then this last one, I'm going to do x times the probability of x. Okay, so here are my 3 bullets. Bullet 1, bullet 2, bullet 3. So bullet 1 is a face card and heads. Okay, so now face card, there are 3 face cards in each suit. Jack has a face, queen has a face, king has a face. So 3 times 4 per suit, that's only 12 face cards. So I'm actually doing the probability. So the chance that this happens, the probability of x happening is face card, that is 12 out of 52, times the heads, that's 1 out of 2. So these 2 events are totally independent. Flipping a coin is going to have nothing to do with the card you draw, so they're independent events, and you just multiply them together. Okay, now x, so big X, I guess we should define, first of all, we should start off defining big X. So big X is going to be the money won or lost. So little x is going to take on these values. Little x can be, you're going to win $6, you're going to win $2, or you're going to lose $2. So this is little x. So that one's $6, this is 2, and this is a -2. So I win $2 if it is face and tails. Okay, so it's the exact same probability. 12 face cards out of 52, and tails is the same as heads. It's 50-50, 1 out of 2. Okay, now the last one, the card is not a face card, so it's a complement of the face, and we don't care about the coin. Alright, so if there's 12 out of 52, the complement of that is 40 out of 52. Okay, now here's what I'm going to do. To find the expected value, you take the number, how much you're going to win, and you times it by the probability. So this is going to be 6 times, if I times 1250 seconds and 1/2, that's going to be 650 seconds, and this is going to be 2 times 650 seconds, and this is going to be -2 times 40 50 seconds. Okay, now your formula. To find the expected value, all you do is sum up each of these products. So I'm going to take this one, this one, this one, add them all together, take the sum of those products, and you're going to end up with, okay, dude, I've already done it on my calculator, and we get this. So mu is equal to -8/13. I think we did this one in class too, and that's like a -615. So that means you're going to lose 62 cents every time you play. So the expected value, so that's A, what we just found, is -62 cents a time. Explain what your calculations indicate about your long-term profits. So that means don't play it, you're going to lose. Stay away from this game. Should you play this game to win money? No. No, bad game. The only way, I mean, it's close. 61 cents a game is not bad. But if you change this from a 6, if you upped the profits, that might change your mind a little bit. Okay, problem 72. You buy a lottery ticket to a lottery that costs $10 a ticket. There are only 100 tickets available. Okay, that's good to know. In this lottery, there are 1 $500 prize, 2 $100 prizes, and 4 $25 prizes. Find your expected gain. So find the average. So same, I think I'm going to do, I like the 4 columns. 1, 2. Okay, so this is going to be x. This is going to be the probability of x. And this is going to be x times the probability of x. Okay, so here are my outcomes. So big X again is going to be money won or lost. Okay, so here we go. Here are my options. I can win $500. I can win $100. I can win $25, or I can win 0. Okay, now, so X is going to be the money won or lost. Now, in actuality, you're not going to win $500. We got to consider the cost of a ticket. So, say I buy one ticket for $10 and they give me $500, so I really only won $490. This is going to be the same. This is going to be 90. This is going to be 15. And this is going to be a -10. Okay, the chances of winning $500, there's only one ticket out of the 100. There's 2 tickets out of the 100. There are 4 tickets out of the 100. So 4, 5, 6, 7. So 7 out of the 100 tickets are winners. That means 93 out of the 100 are losers. So is the prize big enough to entice you to play? So let's see if we can do it. So now we're going to take X and we're going to times it by the probability of X. So it's going to be 490 over 100. This is going to be 90 times 2. That's going to be 180 over 100. 15 times 4, 60 over 100. -10 times 93, so that's -930 over 100, and probably it's not looking good. Okay, now add them all up. If you sum all these up, on your calculator, you're gonna get a -2, and that means you are expecting a loss of $2 for every time you play. So this is not a good game to play. You don't want to play this one. $75. Okay, let's look. This one, I'm going to let you do this one on your own. Pull up your solution book, go through 75. It's really the same things we just did here. You're just going to make a table, except for you're going to have to do it for the different investment options and find which option gives you the best expected value. So an expected value, we want it to be positive. If it comes out positive, that's a game we want to play. So that is the exact same thing as the one we just did. Okay, let's get into the binomial distributions. Binomial distributions, I think these are probably the funnest out of all the stuff we've done so far. So binomial, here's the characteristics of a binomial distribution. There's a fixed number of trials, and each trial has two outcomes, a success or a failure. And then we got all this terminology. So n is the number of trials, p is the probability, that's the chance of it happening, and oh wait, yeah, p, so p is a success, and then q is a failure. So q is going to be the complement of p. So just a couple formulas. I guess we go through this stuff. X is the number of successes. We're only going to worry really about the successes, about the p's. N is the number of independent trials. So X will take on the values 0, 1, 2, 3, depending on how many trials you got. P is the probability, so it's a chance of a success happening. Q is the failure. Q and P add to 1. The average is just N times P. So that's the same thing as the expected value, pretty much. You just take the how many times you're doing it times by the probability. And the standard deviation is this: square root of N times P times Q. Okay, so here we go. 92. A student takes a 10-question true-false quiz. Did not study. Randomly guesses each answer. What is the probability that that student passes the quiz with a grade of at least 70%? Okay, so X is going to be a binomial distribution. N is going to be 10. And P is the probability of, since it's true-false, P is just 0.5. Now, because I want to know this, I kind of want to know the probability of getting at least 70%. So X is greater than or equal to 70%. This is what I want. This is a cumulative distribution. So calculator, here we go. We're going to go menu. Got a calculator, so we're going to go menu, 5, 5. And you're going to have to come clear down to the bottom. The binomials A and B. And you want a CDF. We want a cumulative distribution function. So hit CDF, number of trials. Okay, let's go 10. Chance of a success for each individual trial is the same. Each question is independent. The lower bound. Let's see. Of those trials, I want 7 of them. I want 7 to 10. Because that'll give me my 70%. At least 70%. And there we go. 0.1718. So 0.172. 0.172. That means it is a 17.2% chance. So it's kind of not bad. It's almost a 20% chance, almost a 1 in 5 ish. Maybe it's a 1 in 6. So 1 in 6 kids, if they totally guess, they'll get at least 70. That's pretty dang good. It's on a class of 30. That means 5 or 6 kids are going to get at least 70 with 0 study. Good to be one of those kids. Okay, let's look at problem number 98. You'll remember this one. approximately 8% of students at a local high school participate in after-school sports all 4 years of high school. Group of 60 seniors is randomly chosen of interest. So this is going to be our P. We want the number who participated in after-school sports all 4 years. So this is what we're talking about, and that looks like the P is 8%. So P is 0.08. That means Q is the majority of the kids, and that's going to be 0.92. Okay, so if we define the random variable x is going to be the number of kids who play all 4 years. So the values that x can take on, okay, there's going to be 60 seniors. So x could actually be 0, none of them. 1, 2, all the way to 60. So here's the distribution. The distribution is going to be this. X is a random variable with a binomial distribution with the parameters 60 and 0.08. And n is how many kids are in the sample. And P, each kid has an 8% chance of being called a success, and a success is someone who plays all 4 years. Okay, D. How many seniors are expected? So this is the expected value, and here's what I mean by it's kind of common sense. How many seniors are expected to have participated all 4 years? Well, we already know it's 8%, so we're going to do the 8% and times that by the 60 kids. And so we're going to expect 4.8 of them, 5 of them, to have played all 4 years. E. Based on numerical values, would you be surprised if none of the seniors participated? Okay, so here we go. None, that is going to be this. I want to know, what are the chances that none of them play? So that's calculator. So we're going to go menu, 5, 5. And it is just a probability distribution function, so it's just a PDF. So number of trials, there's 60. Each success has an 8%. And I want this. What are the chances that none of them play all 4 years? And that is 0.0067. I go fall asleep. Okay, none of them. So the chances that none of them play all 4 years, that was like 0.0067. So, dunk. So it's like a 0.7% chance. So would I be surprised if none of them? Okay, this percent right here is really not likely. If I'm a betting man, I am betting that this is not going to happen, because 0.7%, that's so small. So I would be surprised, yes. If none of them participated, all 4, I would be very surprised, because the chances of it happening are very small. So based on numerical values, is it more likely, and this F will make more sense maybe, is it more likely that 4 kids played all 4, or 5 years? Or 5 kids played all 4. So I'm just going to go copy this, hit enter. I'm going to go back out, and I'm going to change it from 0 to 4. Then I'm going to go up and grab it and change 4 to 5. There we go. Okay, so the chances of 4 kids are like 18.7, and the chances of 5 kids are 18.2. So it's more likely 4 kids are going to play all 4 years than it is 5. So we're going to go a little bit, I mean, they're pretty close, but it's a little bit more likely, the odds are in our favor, more for 4 than 5 kids playing all 4 years. Okay, IRS question, this is a good one. So problem number 99 for remember, the chance of an IRS audit for a tax return with over 25 grand in income is, I mean, it's not very likely, it's 2% each year. We are interested in the expected number of audits a person with that income has in a 20-year period. Okay, so let's define the random variable x. X is going to be the number of times audited. So x can be hopefully 0. You could be audited every single year, so x could be 20. So the distribution is going to look like this. X is a random variable with a binomial distribution. The parameters are 20, and I guess we'll call it a success if you're audited. So a 2% success rate. Okay, how many audits are expected in a 20-year period? So I'm going to take the 20 years and I'm going to times that by 2% each year. And that's going to be 0.4. So 4/10 of an audit, not much. What are the chances that someone is not audited at all? So that's calculator. So here we go. We're going to go menu 5. It's a binomial PDF. Number of trials there are going to be 20. Chance for a success is 0.02. And I want 0 audits. Okay, 0.667. So that's actually really good. 0.667. So 66.7%. So 2/3 chance you're not going to be audited at all. That's good. Okay, what are the chances that you are audited more than twice? So the probability that x is greater than more than twice. So it's got to be greater than 2. Or I guess we could say this. Greater than or equal to 3. Because you're not going to be audited. X is only going to take on these whole number of values. Okay, so menu 5, and this is B. It's going to be a binomial CDF, a cumulative distribution. Okay, number of trials still 20. Chance for success is 0.02. The lower bound is going to be 3. The upper bound is going to be 20 in this. We're hoping it's going to be a pretty small rate. Okay, there we go. 0.007. 0.0071. 0.0071. So that is 0.7% chance that you're going to be audited more than twice. So that's not likely at all. Okay, that's it.